Today we're discussing rational functions for section 4.5. So we're going to be looking at rational functions, finding their domain, the graph of the function, also identifying all asymptotes. Then we're going to look at an applied problem involving rational functions as well. So a rational function is any function f that is a quotient of two polynomials. So how we're going to refer to this is as p of x over q of x. General p of x is always our numerator function and q of x is our denominator function. And so the domain, of course, of this type of function, which we've seen in the past, is all inputs of x for which q of x is non-zero. So if we look at something like 1 over x minus 3, we've seen this example a bunch of times, and so we're just going to review this quickly. Find the domain of f. Well, when we're looking at the domain of f, we want to look at when is x minus 3 equal to 0. If I add 3 to both sides, I get x equals 3. That is clearly the number that cannot be in my domain, right? I cannot have a 0 denominator here, and so I cannot have x minus 3 equal to 0, which means x not equal to 3 is my domain. And in interval notation, we reference that by saying it's negative infinity to 3. I use parentheses to not include 3 itself, like skipping right over the number 3, pick back up again at 3.01, and go on to positive infinity. So that's how we represent the domain of f. But what we're really picking up today that's the new thing is that when looking at the graph, if we plot the line x equals 3, which is just what I've dashed in there, then you're going to start to see an asymptote with your function, where your function gets really close to that line, but never actually crosses it. So to formalize that, for a rational function, f of x, it's p of x over q of x, where p and q are polynomials, also assuming that there's no other common factors. There's nothing that I could reduce or cancel for my numerator and denominator. Then if my number a is a 0 of q of x, the line x equals a is a vertical asymptote for that function. And note that x equals a cannot be a 0 of that numerator as well, or that means that they actually do have factors in common. So we're going to check that our number a is a 0 of the denominator and make sure it's not a 0 of the numerator. And then we know that we'll have vertical asymptote. So let's see an example. Determine the vertical asymptotes of this function, 2x minus 11 over x squared plus 2x minus 8. And to find those vertical asymptotes, what we're going to do is check if x squared plus 2x minus 8 can be factored. So if we factor this standard quadratic, it goes into two binomials like this. We want to think about, well, what multiplies to 8 and adds to 2? And that, of course, is 4 and 2. And the plus will go with the 4, the bigger of the two numbers. So we get x plus 4 and x minus 2. And so our function f of x is then 2x minus 11 over x plus 4, x minus 2. So to find out where the actual asymptotes are, we're going to take that denominator and set it equal to 0. We can look at x plus 4 equals 0, and we get x equals negative 4. We look at x minus 2 equals 0, we get x equals 2. So those are our two asymptotes. Notice that when I plug either of those back into my numerator, I do not get 0. So I know that they're both asymptotes. Looking at the graph, that's exactly what these dashed lines in here represent, are the asymptotes of this graph. We can also have horizontal asymptotes. So we can have a line, y equals b, that's a horizontal asymptote, if either of these following cases are true. Where as x goes to infinity, so that's how we read this, x goes to infinity, x gets really, really big, then our function starts to settle in on a single number. It starts to horizontal or level out. And the same thing can be true if x gets really, really small, so we're going all the way left on the axis, and f approaches some number b, again leveling out. Those are what we call our horizontal asymptotes. We have a pretty easy way of checking for horizontal asymptote. We're just going to look at the numerator and the denominator of our rational function and look if they have the same degree. If they do, then we just take a over b as our asymptote, where a is the leading coefficient of p of x and b is the leading coefficient of our denominator q of x. So let's see that in practice. Oh, before we get into practice, let's talk about the other two cases actually. So if we have the first case being what I had just said, if the degree of q and p match, then the horizontal asymptote is y equals a over b, where a and b are the leading coefficients of p and q. If the degree of p is actually smaller than the degree of q, so let's say I have an x squared leading term on top of an x cubed leading term, then the horizontal asymptote is actually the x-axis. And if, of course, my degree of p is larger than the degree of q, then there's no horizontal asymptote. So now we'll see examples of each of these. So first off, we always want to identify our leading term. The leading term here is x cubed and 4x cubed. Those are both degree 3. So degree of our p of x is 3. The degree of q of x is also 3. And so then our horizontal asymptote is y equals, horizontal, y equals 1 over 4. Notice the coefficient here is 1, the coefficient down here is 4. So our horizontal asymptote is just y equals 1 over 4. And that's it. Looking at the next example, our next leading term is negative 2x on the top and x cubed on the bottom. So here my degree of my p of x is 1, and the degree of q of x is 3. If you remember our rule from before, if the degree of p of x is less than the degree of q of x, then my horizontal asymptote is y equals 0, or the x-axis. Now for our third case, I can have, well, here's my leading degree on top, here's my leading term on the bottom. So of course, if I have my degree of p, which is 4, and I have the degree of q here, which is 2, then of course I have 4 greater than 2, which means that there is no horizontal asymptote. And that's what all of those three cases look like. And it doesn't matter what any of our trailing terms are. I don't care about the minus 7x squared and the plus 13. None of it has mattered in any of these examples, because all we want to look at is what that biggest term is doing. It sets the trend for the overall function. So now we're going to work on actually graphing a function like this. We're going to find all its asymptotes. We're going to draw the asymptotes with dashed lines. We're going to plot some of the points. Then we can actually draw the curve. So when looking at something like g of x equals 2x squared plus 1 over x squared, we want to find the vertical asymptotes first. We want to look at where x squared equals 0. Always want to set our denominator equal to 0 for these. So of course we get x equals 0. For our horizontal asymptotes, we are comparing our degrees. The degree of p of x here is 2. The degree of q of x is also 2. Therefore, the horizontal asymptote is at y equals 2 over 1, or just 2. Notice coefficient here is 2, coefficient there is 1. So there's our horizontal asymptote. Now let's jump to our next slide and actually draw these. We have x equals 0 as our vertical, and we have our horizontal as y equals 2. So drawing those in here, I'm going to draw them in blue. My vertical asymptote's at 0, so I have a dashed line down the y-axis at x equals 0. And then at y equals 2, I also have a horizontal asymptote. Looking like that. And so now if I plot these points that we have on the right, then we're actually going to be able to start to pick up our graph and see what this curve is going to look like, kind of what shape is going to be behaved here. So I'm going to plot -2 and 2.25, which is about right here. And then I'm going to plot -1.5 and 2.4, which is a little bit higher. Now I'm going to plot -1.3 right here, -0.56. Okay, so we're really starting to shoot up here like this. Now I have 0.56. So I don't think these two connect, but we are going to jump over, see what's happening on the other side of the graph. And then 1.3, 1.5 and 2.4. And then 1.2 and 2.25. Just like this. And so if I know it must level out, and I know it must rocket up towards the y-axis, I know we're looking at a graph that's shaped like this. And it just levels out. It never crosses the axis. It never crosses the asymptote, just levels out down like that as well. And so typically you can start to pick up your shape based off of kind of where it's going to fall and how close to the asymptote it'll go, based off just plotting a few points. Now, another type of asymptote that can happen is an oblique asymptote. And this happens when the degree of p of x is just one more than the degree of q of x. And what this kind of looks like is if I have a shape kind of like this first one, where you can see that it's clearly not a line in the middle, but it's becoming very, very close to the line as we look at what's happening up here and what's happening down here. It's very much leveling out at a specific line that we would like to represent. Same thing is going on for this example in here. You see how after this craziness in the middle is over, it really starts to level out, looking just like a straight line. So those are what we call oblique asymptotes, and we need to be able to solve for those as well. So here's an example. Find all the asymptotes of this function. So of course we can find vertical asymptotes as well, which we should start there. And we want to think about then when x minus 2 equals 0, and we get the line x equals 2. So there we've found that one out. Now we want to think about, okay, is there a horizontal asymptote or is there an oblique asymptote? And which we can only have one of those two. So notice I have a 2x squared on top and an x on bottom. Those differ by exactly 1 degree. X squared is 1 degree larger than x. And so I know I can have an oblique asymptote here. What we're going to do then to find that is actually do a little bit of long division. You could do your synthetic division here, but it gets a little bit trickier when we have bigger terms down the road. So I suggest sticking with long division here. When we do that, I'm looking at 2x squared minus 3x minus 1 divided by x minus 2. And to solve this using long division, I always ask myself, what times x gives me 2x squared? And that's just 2x. So we carry out that multiplication. 2x times x is 2x squared. 2x times minus 2 is minus 4x. And we subtract the whole thing. Now when I look at 2x squared minus 2x squared, that's gone. Now I have minus 3x plus 4x, which is just x. Notice the minus 3x minus a negative 4x makes a positive 4x. And the negative 3x plus 4x is what gave me the x. Now I drop the 1. Now I just ask myself, what times x minus 2 gives me x minus 1? For this one, we're going to pick up a 1 because 1 times x gives me x, which is the term I'm trying to match. And 1 times a minus 2 is a minus 2. We subtract this whole thing. We have minus 1 minus a negative 2, which is just 1. So that means I have remainder 1 here. What that really tells me is that f of x can be written x minus 2 times 2x plus 1 all divided by x minus 2. right? That's what we get out of that, factoring out that top numerator. At least factoring it as much as we can with long division. Yes, we have a remainder here. What we end up getting, though, if we distribute the x minus 2 on bottom, is x minus 2 times 2x plus 1 over x minus 2 plus 1 over x minus 2. But what happens with that first term is that the x minus 2's cancel, and I'm left with 2x plus 1 plus 1 over x minus 2. 1 over x minus 2 is actually a function that goes to 0, right? That's our asymptote where I have a larger degree in the denominator than the numerator, so I know that asymptote goes to 0, which means that term is gone, and I'm left with this 2x plus 1 business. So that 2x plus 1 is actually the line that gives our oblique asymptote. So as soon as you plot that line, whatever you had left over, that's what picks up exactly what line your function settles in on. So carrying out that process, doing the simplification, canceling out the term that goes to 0, we're left with 2x plus 1, and we have found our oblique. So in summary, for a rational function p of x over q of x, we can have a vertical asymptote where the denominator is set to 0. We can have a horizontal asymptote where we're comparing the degrees of our p and our q. Or we can have an oblique asymptote, which occurs when the degree of p of x is just one more than the degree of q of x. We do our long division, cancel out the remainder part, and the result is our oblique asymptote. And just note that we can only either have a horizontal asymptote or an oblique asymptote, not both. Okay. As soon as you have one, it cancels out the other one. A couple of other things to note is that a graph can actually cross the vertical asymptote, it can actually cross a horizontal asymptote. It doesn't have to, but it actually can happen. So you could see a function, let's say it has an asymptote somewhere along here. You can actually see a function go like this, drop down, scoop back up, and then level out again at the same asymptote. So things like that can happen where it just does a quick cross and then levels out again at horizontal. Vertical asymptotes, though, you never cross a vertical asymptote. It's like an invisible force field. As soon as it's there, we draw it with a dashed line, looking something like this. Your function can never cross it. It can have multiple different gaps like this, or it can shoot down at the same angle, or it can come up from here and go down, but it can never, ever cross that line. All right, now we have our 6-step process for graphing rational functions. What we're going to do, anytime you're given just a general rational function, you're going to start with determining what is the domain of this function and what are my vertical asymptotes. Let's sketch those and get those down. Then we're going to find if our function has any horizontal or oblique asymptotes and sketch those. Then we're going to find any zeros of the function that'll help us know exactly where we're crossing the x-axis, which you want to use your numerator for that. Then we're going to find our y-intercept and some other function values until we at least have a general shape of how this function's behaving. Then, of course, we got to draw the graph. So let's start with this example, 2x plus 3 over 3x squared plus 7x minus 6. Determine the domain of the function and sketch any vertical asymptotes. So the domain of this function is wherever our denominator is 0. So we have 3x squared plus 7x minus 6 equals 0. We got to factor this. So I have a 3x and an x. And I have things that multiply to 6. I have 2 and 3, or 1 and 6. If I have a 1 and a 6, I could have an 18, or a 1, that wouldn't work out well. If I have a 3 and a 2, then I could have a 2x and a 9x. There's supposed to be an x here. A 2x and a 9x. Oh, that can make a 7x. Okay. Remember that you have to multiply these inners and outers in order to think about How do I add to that middle number? Okay, well here, if I have a minus 2x and a plus 9x, that will give me a plus 7x overall. So that's our factor denominator. Defined the vertical asymptotes, which also informs our domain. We got to set each one equal to 0. 3x minus 2 equals 0, and x plus 3 equals 0. Adding 2 to both sides over here, I have 3x equals 2, so x equals 2/3. Here, if I subtract 3 from both sides, x equals negative 3. Those are our two vertical asymptotes, and so our domain is all numbers leaving out those two, essentially. Now we want to find our horizontal asymptote or our oblique asymptote and sketch it. Notice here, looking at the degrees, I have a 2x over a 3x squared. That means that the degree of p of x here is 1, and the degree of q of x here is 2. Well, that means that I'm in this less than world where p of x is less than q of x, which means that my only horizontal asymptote here is the x-axis, or y equals 0. Now find any zeros of the function. Hint, find the zeros of the numerator. So we want to look at 2x plus 3 equals 0. And so we subtract 3 from both sides. They get 2x equals negative 3. And so x equals negative 3 halves. That's one of our zeros, negative 3 halves, comma 0. So we have a vertical asymptote at x equals 2/3, x equals negative 3. We have the horizontal asymptote at y equals 0. And we have a 0 for our function at essentially the point negative 3 halves, comma 0. So we've picked up this much so far. Let's keep going. Next, we're going to find the y-intercept. For that, we want to plug in x equals 0. We're looking at 2 times 0 plus 3 over 3 times 0 squared plus 7 times 0 minus 6. So that's going to be 3 over negative 6, or negative 1/2. So that's another point for us to help us out on this problem. Then, of course, if we want some other function values, we can look at our graph here to get the general shape. Or I didn't mean graph, I meant table. We can look at our table here to help us get the general shape. I would plug all of these values in on your calculator and get the y values. Use the table function on your calculator. It would be terrible to have to plug all of these numbers into 2x plus 3 over 3x squared plus 7x minus 6 each time. That would take a lot of time. So please use the table function on your calculator that we've talked about in the past. Reach out to me if you have any questions on that. Once we have this table, then we can take it over to our graph and see what it actually looks like. So if I graph negative 4.5 and 0.26, negative. So negative 4.5 is about here, and 0.26 negative is about there. Oh, you know what? I jumped right into the points. Let's make sure we actually draw our asymptotes. So I have x equals 2/3 and x equals negative 3. So let's draw those first. And I'm going to change my pen to blue. Here's our line at negative 3. And then again at 2/3. So there's 1, 2/3 is right in here. And then, of course, at 0 is our horizontal asymptote. And then going back again, we have negative 3 halves, comma 0, and 0, negative 1/2 as our points. So negative 3 halves, 0, and then, what was the other one? Negative 3 halves, 0, and 0, 1/2. That was the other one right in here. So we should also see it crossing those points. Now let's jump in and graph all the other points on our table. kind of now we have our grid lines kind of expecting where our shapes are going to go. So this is when we jump into some points. Help us out. So negative 4.5, negative 0.26 goes right here. Negative 3.25, comma, negative 1.19. So negative 3.25, here's 3.25, and negative 1.19 here. And negative 2.5, 0.42, negative 2.5, 0.42, and negative 0.5, negative 0.23, .5, negative 2.29, be about right here. And then 0.75 is at about 4.8, around here. And what's next? 1.5 is at about 0.53. 3.5 is 0.18. 3.5 is just about right here. And you know what? Did I mark something incorrect before? I did. Notice I had 0, negative 1/2. I have that in the wrong place here. 0, negative 1/2 would make a lot more sense right here, I think. It can be a little bit hard to pick up the graph, but we have to just remember the rule that it cannot cross our vertical asymptotes. So if we're not going to let it cross our vertical asymptotes, then we kind of get an idea for where this function is going to go. Where this point here tells me, oh, I must stay in between these two, which means my function must look like this. For this function up here, I see the points kind of coming down like this, shooting across and going back down. And so, of course, it must have come from up here then. Similarly, then, I must have this corner because it cannot cross the axis. And so it comes down like this. And so just filling in the dots and picking up the general trends, we can kind of make assumptions about where the rest of the shape must look like, just knowing that it must hit the asymptotes in a certain way. And we can connect the dots and pick up our actual graph. So normally we would not be able to graph something like this. Even with several points, we would have had to get really minuscule with the points in order to understand what this looks like. But because we know where the asymptotes live, we can easily draw this graph now. So moving on to the next one, let's see another example. Here we have x minus 2 over x squared minus x minus 2. We're going to determine the domain of this function and sketch any of its vertical asymptotes. And of course, go through the rest of the steps that we have. So for this function, of course, we want to factor our denominator, find out where it equals 0. X squared minus x minus 2. As we factor that guy, we're looking at x and x. I'm thinking about things that multiply to 2. Of course, that's 2 and 1. They clearly have opposite signs, and the minus goes with the 2. But then look what happens with g of x when I have x minus 2 over x minus 2 times x plus 1. Well, clearly those two can cancel, and so it's equivalent to have x plus 1. However, you want to note still that we cannot have x equals 2 or x equals minus 1 in our domain. So it does simplify to 1 over x plus 1, but we still have the domain of 2 and negative 1, or excuse me, these two are not in our domain, essentially. X equals 2 and x equals negative 1. So that means that only x equals negative 1 is an asymptote, because x equals 2 is a 0 of our numerator, and we said that can't happen if we're going to have a vertical asymptote. So x equals 2 is removable, essentially is what we say, because we're able to cancel away its factor. We're left with x equals 1 as our only asymptote. Now looking at our horizontal or oblique asymptotes, we again have the case where x squared is our denominator, our largest term in our denominator. And so, of course, it's setting the trend for the overall function. And we know that this function is then going to go to 0. So to write that down, the degree of p is 1. The degree of q is 2. And so therefore, horizontal asymptote at y equals 0. Now we want to find any zeros of the function, which of course are zeros in the numerator. And in this case, it's x minus 2, which implies that x would need to equal 2, but that's not in our domain. So that is not a 0 of our numerator, because again, we can't actually plug that into this function. We would have a 0 denominator. So no other zeros to worry about here. Moving on, if we look at our y-intercept, here we plug in x equals 0, and we get 0 minus 2 over 0 squared minus 0 minus 2. That's minus 2 over minus 2, which is just 1. So we have 0, 1 on our graph. And then we're going to find some other function values to find the general shape. And I filled in several on the table on the right in order to help us out. So now let's try to draw this graph. First off, we're going to remember this time, though, that we have a vertical asymptote at x equals -1, horizontal at y equals 0, and the point 0, 1. So starting with the point 0, 1, let's make sure I do it right this time. And then drawing some of our asymptotes, we know we have y equals 0 as one of them. And then we have, what was the other one? X equals -1 as the other one, right in here. There we are. So now as we plot our points, we plot those in blue too. I have -3, -0.5, -2, -1, -1.5, -2, -1.25, -4. I think we can see where that trend is going. -0.754. We have jumped. -0.52. And 0, 1 we already have, and 1, 0.5. And so you might agree we can pick up exactly what this function is going to look like. Filling in our line in red, it's going to, of course, come from our axis, loop down through these points, and shoot down through our other vertical asymptote. And then, of course, it's going to jump up top here and swing down through and hit our horizontal asymptote. Just connecting the dots at this point, following the trends. That's what this graph looks like. Now, you might notice that some of these points are not some of them, all of these points are actually coming from 1 over x plus 1. And that's because that's really what function we needed to graph here. It was easier to focus in on those points. However, we want to be careful to remember the fact that x equals 2 is also not in our domain here. It was removable. And so we actually need a big old hole in our function at x equals 2, which would look just like this. So you always want to go back for that detail, make sure you didn't miss any holes. We do need to actually go and draw that on the graph. And that was the removable factor, the x minus 2 that got canceled away. It creates a hole in our graph right where we see it now. Now for our next example, we're looking at 7x cubed over x squared minus 16. This is going to be an example with an oblique in it. First off, though, we're going to start with the domain and any vertical asymptotes. So, of course, we're going to take x squared minus 16 and factor it. This is our difference of squares problem. X plus 4, x minus 4. And so then, of course, we get x equals -4, and x equals positive 4. They're both not in our domain. So if I were to formalize our domain, negative infinity, negative 4 to 4, and 4 to infinity. Essentially, pick up your pencil at negative 4, keep going along the number line to 4, and then jump over 4 again and keep going on to positive infinity. So that's our domain. And then, of course, our asymptotes were these two, x equals negative 4 and x equals 4. Those are vertical asymptotes. So now to find our horizontal asymptote, we know that there's no horizontal asymptote because the degree of our top term is bigger than the degree of the bottom term. So there could be an oblique asymptote. And what we need to do to figure that out is divide x squared, minus 16 into 7x cubed using our long division. So jumping in here, we want to think about what times x squared gives me 7x cubed. And that's, of course, 7x. If I carry out that multiplication, I'm looking at 7x cubed. I subtract, 7x cubed. Before I subtract, I need to carry out the 7x multiplication with the minus 16. And 7 times 16 is, pulling out the calculator, is 112. So that is minus 112x. If I subtract this whole thing, I'm left with 112x. So that is actually our remainder. It looks strange because it's the same degree as 7x, but it's actually a degree less than x squared minus 16. So it is, in fact, our remainder. We are, in fact, done. That means then that f of x can be written. Its numerator essentially can be rewritten x squared minus 16 times 7x plus 112x. And my denominator did not change. Well, now if I distribute my denominator, I'm looking at x squared minus 16 over, times 7x. X squared minus 16 plus 112x over x squared minus 16. Now, of course, this x squared minus 16 cancels, and I'm left with 7x. And this term in here doesn't matter. It goes to 0. Its horizontal asymptote has a larger degree term on the bottom. So the horizontal asymptote rule says that that must go to 0, which means all of this simplifies down to 7x. And that is our oblique asymptote. It's just 7x. Now, any zeros of the function, well, that would be an error for zeros of the numerator. So we're looking at 7x cubed. And if that equals 0, that would give us x equals 0. And so naturally, that's the 0.00. So if I have my y-intercept, I would normally think about, well, when does x equal 0? But we just found that exactly gives us the 0.00. So we have, in summary, vertical asymptotes at negative 4 and 4, an oblique asymptote at y equals 7x, and then of course we must go through the origin 0, 0. So let's get these things plotted onto our graph. I must have my vertical asymptotes at negative 4 and 4. Putting those on first, negative 4 sits right through here, and 4 sits right through here. And then, of course, y equals 7x. It's helpful to have 2 points to plot here. If I plug in, negative 7 here, I get negative 49. And if I plug in 7, I would get positive 49. It's just a really easy, quick multiplication with 7, right? I plug negative 7 into 7x, and I get negative 49. If I plug 7 into 7x, I get positive 49. Quick way to get my 2 points. So I can draw my oblique asymptote y equals 7x. So if I go to negative 7, negative 49, which is right down here, and I go to positive 7, positive 49, right in here. And so my dashed line should go through this. And I threw in the origin there as well for 0, 0. So that's the general shape of our graph. Now it would be helpful to get a few more points. So to determine the rest of the shape, it's often very helpful to focus in on our asymptotes and pick up a lot of extra points. If I try to plug in -4 here or 4 down here in a table, it would actually give me an error in my calculator because we already saw we can't plug those values in. So I like to pick up half step or quarter steps above and below that asymptote in order to see what's really going on with the function. So you see some of the points written out here, and actually I did this in a larger scale in the next slide. You only need enough points till you really get a good idea for where the graph is sitting. You can only pick up so much by staring at your graphing calculator on that really small screen. And you need to be a little bit more accurate with your placement of points on the actual test if I ever ask you to fill in points. So, or fill in a graph. So I highly recommend just, writing down a table and using the table function on your calculator to be able to get enough points to draw the graph. So if I were to graph all of the points that I wrote on the left here, which yes, there's 20 of them, but it can go by pretty quickly, again, using that table function on the calculator. And when I graph all of these points, now you can clearly see the shape of the graph start to appear. And I know that I must respect my asymptotes. And so looking at the dots, if I were to actually fill this in, I must follow along. Let me do this in red. I must follow along the graph, the line here, looping through my points and hitting this asymptote down here. I must have then jumped up here, coming down along that asymptote, leveling out and still going. And then I must have jumped up here and followed the trend out on, again, that same oblique asymptote. Now, I know it looks super strange because my oblique asymptote crosses right in the middle at a very different direction from my function. But this is actually correct. If I show you the here's the filled in version from Desmos of this function. This is exactly how our function goes, and we still have that weird spot in the middle here. But the asymptotes don't care about what's going on in the middle. They care about what's happening on the ends. So again, the middle doesn't matter, the ends matter. So you can see how the ends are really starting to head off and trend exactly towards where our oblique line sits. And that's the important factor here. So an example with an application here. Here we're given a function n of t, where t can only be greater than or equal to 15. This function gives the body concentration in parts per million of a certain dosage of medication after time t in hours. Find the horizontal asymptote of the graph and complete the following. So, only using kind of what we've learned in lecture today. We don't have to worry so much about the meaning of this application right now. We want to think about horizontal asymptotes. I see that my degree of my numerator is 1. The degree of the denominator is 1. So therefore, for my horizontal asymptote, I'm looking at 0.4 over 5. And 0.4 divided by 5 is 0.08. So to fill in this statement, I would say that my function approaches 0.08 as t grows to infinity. So that is how we represent our horizontal asymptotes sometimes. We say, oh yes, as my t value gets really, really large, so I'm really far to the right on the graph, I know my n of t is settling in on the number 0.08. But what that means in terms of this application is that my value over time, the value of that drug in someone's body over time is going to settle in on 0.8. That means that there is always 0.08 ppm in someone's body as time goes on. So essentially, it never leaves the body, this medication. That's what this function is telling us. It settles in on 0.08 ppm, and it doesn't go all the way to zero, which is kind of interesting, I think, given the function that we see there. So as always, guys, if you have any questions, please reach out. I'm always available by email, and let me know if you have any questions, especially with exam 2 coming up next week.